All right. Thanks guys for last week. We took a week off. Um, no homework today, so if you haven't gotten your homework in, get a little more time. But I appreciate the 5 or 6 people that got it over. It's tough, a 3-day weekend, a 3-day week, and all that. Hope everybody had a good holiday. Again, this is we're heading into the Green Mile part of this class. A lot of hypothesis tests and um, inferential statistics and all that kind of stuff. And you'll find it's not that hard. They just try to make it hard, with the terminology and stuff. Um, I think we can make it digestible. So I'm going to start with the math practice. I got an update. I just got Paul. So there he is. Again, you got a little more. There's no homework today. So you have a little bit more time. I think I had Joanne Marie and John's homework like 10 minutes after class ended last time. Um,
Not true. Come
Pretty
on.
close, pretty close. But they sit up in front. They're always early. So the homework was again, for those of you who have handed it in already, is we're basically doing the same thing. We have this whole population of 800 plus weeks of data, and we got a bell-shaped curve. And by doing a much smaller time period, last couple of years, 2.5 years, things get a little bit tighter. And, we're no longer at, now our min's at 170, and our max is at 189, and our mean has dropped 3 pounds. Standard deviation has dropped a full pound. So it's just compressing and getting more. My process is getting more predictable, more stable, because there was a huge range. It was 10 pounds difference in range between the two data sets. So the way I did it, for those of you who haven't done it yet, I just started down the bottom, at 20, 22. And kind of just did exactly the same thing. Again, those of you that already sent it in, great. Appreciate it. And I think it's going to help. Next week we're going to do a little more homework. I think we're doing normality testing next week, and then about halfway done with the homeworks. It just makes it better, easier if you stay on top of it. So today we're going to talk about a couple different concepts. We're now into the analyze phase. So now we have a problem that we've defined. We have something that we've measured. We've measured that problem, and now we're in the part where how do we interpret what we've measured, and what are the smart steps we can take to improve the process. And one of the things we're going to talk about today quite a bit is something we call inferential statistics. And basically all that means is based on a sample, can I make an inference about an entire population, right? Because most of the time it's not practical to sample the entire population. For example, if I want to know what the average IQ is in the world, the population would be, every single person measuring their IQ, or I would start doing some samples, and then I want to be able to make some inferences on those samples. And this is kind of the beginning of the next week or two. We're going to be talking about hypothesis tests, where we're trying to make some guesses, some educated scientific guesses about our data and what it's telling us. Like we talked about with descriptive statistics, just by looking at just the date and the weight, for example, there's not a lot of information there. It doesn't tell us much. It doesn't tell us what we need to do. So inferential statistics, which is going to be pulling information out of samples of populations. All right, and there's a whole bunch of different types of hypothesis tests. So I thought it'd be good that before we get into the PowerPoint today, to kind of just go through an example of how a hypothesis test works. All right, because we're going to be doing the same steps over and over and over and over. So I think this is a really good timely example. The average temperature since 1950 in Connecticut is 87.5 degrees Fahrenheit. And it has a standard deviation of 3.5 degrees. So remember, standard deviation is the average amount of temperature of degrees away from my mean, my average. Okay. It's the average distance. So it's kind of like it's looking at the spread of the data. So the standard deviation is about 3.5 degrees. And that's based on since 1950. So that's what, 74 years times 30, 31 days in July. So that's a lot of data, right? The temperature was on July 7th was 94 degrees. So the question becomes that we want to ask is, with a 95% confidence level, I want to be 95% confident, was July 7th temperature statistically significantly different than the average for the month of July since 1950? All right. And statistically significant difference is different than practically significantly different. Practically significantly different is that it feels different. It's just I'm more uncomfortable, or from a statistics standpoint, what we're looking at with a 95% confidence level is if doing math, with the 95% assurance, is it significantly different? So the way this works is the first thing we're going to do is clearly define the objective and the confidence level. So the objective is that we want to know if July 7th was statistically significantly different than the average for the month of July since 1950, at 95% confidence. And you're going to hear things in the presentation about alpha and beta and all kinds of different ways of saying confidence level. The one I like is, as you're going to see, is rejection region. And we're going to get into that in a second. And then we're going to look at, second, is it going to be a one or a two-tailed test? So when I do this test to try to understand if July 7th was statistically significantly different than the average, is it a one-tailed test or a two-tailed test? And all that means is, if I had said to you, was July 7th statistically significantly hotter than average, then we're talking about a one-tailed test. We're just talking about the right side of a graph that you're looking at there, right? If I had said, was the day's temperature statistically significantly cooler than the average for the month of July, which would be kind of silly if it was 94, that's again, it indicates a one-tailed test. All I'm asking is it's significantly different. So that automatically tells me it's going to be a two-tailed test. We're going to be testing both sides, right? The plus and the minus. The side on the right of the mean, and also the side on the left of the mean. Next thing we're going to do is we're going to formulate a null and an alternate hypothesis. A null hypothesis is always going to be the status quo. In other words, I like to think of it as innocent until proven guilty. So the null hypothesis here is going to be July 7th was not significantly different, not statistically significantly different than the average. That's my null. All right. Now, my alternative hypothesis is going to be, yes, July 7th was statistically significantly different for the month of July. All right. So those are the steps so far. Define the objective and the confidence level. And you can do it with any set of data. Formulate a null, which is always going to be the status quo, or think innocent until proven guilty, and an alternate hypothesis. The only objective of hypothesis testing is to reject the null hypothesis or not. Either we're going to reject the null hypothesis or not. Okay. And then we're going to select a test distribution based on our data. So think about it. If I have 74 years worth of data times 31 days in a month, I have pretty big data set, right? So that average of 87.5 degrees, generally you're gonna have a bell-shaped curve there, because you're gonna have a couple temperatures warmer, a couple temperatures cooler, maybe 10, maybe 10 degrees warmer, 10 degrees cooler, maybe on some years, whatever. But largely we're looking at a bell-shaped curve just because the amount of you can pretty much predict what July is going to look like in Connecticut in terms of what the temperature. So I have to select a test distribution. So in this case, I'm going to select a normal distribution because I'm looking at data that I measure, right? And then from that, I'm going to calculate a test statistic. And for normal continuous data, I'm going to look at what we call a Z statistic. And all it is the statistic. This is my test statistic. So I have to do a little bit of math and then compare that to a critical value that comes out of a table. All right. So there's tables for every single one of these tests. So if I don't have a normal distribution, or if I'm looking at discrete data, things that I count, I'm going to use a different table, either a chi-square table or a binomial table. But all I need to kind of start to understand is, and we're going to kind of go through this the next couple of weeks, is, all right, so what kind of a data am I looking at? And with that, what formula did I use to get my test statistic? And then once I get the test statistic, I'm going to compare it to a number that I'm going to pull out of a table, which we're going to do right now. So in this case, the formula is Z, which is going to be my test statistic for normally distributed continuous data, is equal to X, which is going to be my 94 degrees. That's the one in question, minus my mu, which is going to be the average temperature, the average of all the temperature readings since 1950, 87.5, divided by sigma, which is going to be my standard deviation, 3.5 degrees. And with that, I come up with a test statistic. I do the math, 94 minus 87.5 divided by 3.5. I come up with 1.857 as my Z-score, which is my test statistic. So the way I like to think about it is now I have to find out, I got to compare that number to a critical value. And if you Google statistical tables, you'll find T tables, Z tables, chi-square tables, all kinds of tables. They're all available, really easily available. And all we're going to do there is we're going to set up the goalposts. So let's pretend that this is a distribution of the temperature. And there's the average, right in the middle of the bell-shaped curve. And I'm going to find out where the goalposts are. Where does my rejection region begin? And I call it a rejection region, RR, on both sides, because if my actual test statistic lands in that rejection region, then I can reject the null hypothesis. And the null hypothesis is that there's no statistically significant difference on July 7th from the rest of the readings. All right, so go in the table. There's my Z down here on the bottom. I'm going to go across the 95% confidence level. Or the same thing, you can also see up here, it says 0.05 for alpha level. That's the same thing, right? So it's 95 and 0.05 are the same thing in terms of getting the goalpost. So my goalpost is going to be set at 1.96. So I drew on here, as you can see, on the right side, plus 1.96 sigma, right there. And on the left side, minus 1.96. And my test statistic was 1.857. So where is my 1.857 going to land on this graph? Anyone? The 1.96 is what begins the rejection region.
It'll be within the bounds.
Exactly right. Excellent. So that means, all it means is it's not in the rejection region, so I cannot reject the null hypothesis. So even though it felt like hell the other day, it's not statistically significantly different than the average for the month of July. And that's kind of everything we're going to be doing over the next 2-3 weeks, really. In terms of hypothesis testing, you're going to come back to the same sequence of thinking. Clear defined, is it one or two tails? Null and alternative hypothesis. What kind of data do I have? Calculate a test statistic, compare it to a table, and then either reject the null or not. And that's as simple as it gets. That's it. That's all there is to it. Any questions about this? We're going to see a bunch of this over the next couple weeks. Again, because I want to be able to make inferences about large quantities of data. Let's go into the fun PowerPoint. And this is like pretty repetitive. I think I love starting with the with the math practice, because I think it just makes so much more sense, so much easier. So congratulations, you are exactly 2/5 of the way to your coffee mug and a certificate suitable for framing. But again, we're going to define the problem and objectives. What do we need to improve? And then how do we analyze and define the factors of influence? And again, we're going to spend most of our time in problem solving, whether you call it Kaizen, A3, problem solving. We want to spend most of our time in the DMA. And if we do a really good job here, then the I and the C roll off the tongue. And both of those are only 2 weeks. So there's 3 weeks defined for this class, 3 measure, 3 analyze, and then 2, because we want to make sure that we do a good job in these 3 areas. So it's about finding the top 1 or 3 causes of the problem being addressed. And it starts with the team input regarding potential causes. And we use statistical methods, isolate the top 1 or 3 causes. And we're going to cover today multivariate analysis quickly. We'll talk a little bit about classes of distribution, understanding inference, sampling techniques and uses. And then next week, we're going to get into kind of we're going to cover again what I just went through, but we're going to get into practical and statistical significance, alpha and beta risk, types and decision, reading tables, and then testing for normality, and then all kinds of tests, all kinds of tests. So there's another statistical notation. I'll have the PowerPoint slides to you for Analyze today after class, in a PDF format. If you ever want to refer to this again, I'm not all that interested in you guys doing longhand test statistics, using any of this stuff. It's good to see it and understand how it all comes together, but generally, I don't think we're going to spend a lot of time with that. So we're talking about patterns of variation. Let's start with that, multivariate analysis. And I'm going to skip ahead for a second. So basically, where does variation come from in a process? And there's 3 variation sources, classifications of sources. One is positional, one is cyclical, and one is temporal. All right. So it's really important to know what the source of variation is in our process, why we're not getting a predictable result from a process. The multivariate analysis is a really cool graphical tool that allows us to see a whole bunch of X's at once together, okay? It's a great tool for early root cause analysis, and families of variation can exist in a subgroup, between subgroups, or over time. And now I'll go back to the cookie idea. So I want to say, listen, I want to make sure that my cookies are consistent. So there's, again, within the unit, I'm going to make on 2 separate days, I'm going to make 2 batches, right? So I make 2 batches on day 1, 2 batches on day 2. And my cookie variation is defined by I have the exact same number of chips in each chocolate chip cookie. And also they all have the same consistency in terms of degree of cookedness. Some aren't real soft and others are rock hard, so that's how I'm kind of defining in my cookie variation. So variation within the unit is if I make that first batch on day 1 and I get half the batch has, 10 chips in it, and some of them have 6 or 5 or 4. That would be variation within a unit. Or maybe some parts of the cookie some of them are chewy, some of them are hard, whatever. Well, that's going to kind of point me in a direction of what am I looking at, right? Am I looking at how I'm distributing the chips into the dough? Am I looking at, is my oven consistent in terms of how, looking at how I'm cooking them, the size of the cookie maybe, in terms of how they're cooking, but it's going to point me in a direction where I can start to analyze the variation. And then the second one is on day one, and this is going to be, so we got variation within unit, between units, and between unit would be batch 1 and batch 2 have that same variation. Okay. Now I might be looking at other things, again, maybe the size on the second batch. Maybe did someone else do that second batch? Might be a whole bunch of, did I open up a new package of dough? Who knows what? And then temporal is going to be variation that happens over time. And this is where we start thinking about, is the variation between shifts? Does it vary over time, where all of a sudden, the piece of equipment or instrumentation hasn't been calibrated and it goes out of whack or something. But those are generally the 3 sources of variation that we're going to look at. And I actually use this one. This is kind of what it looks like, because it's not only, pieces of thing within the piece, location in the batch or over time, but my wife, when she owned a frozen yogurt shop, there's consideration about maybe getting a couple more of them and looking at square footage, location, profit, and being able to, the beauty of this is be able to look at many variables at the same time visually. Because generally I'm a chemist, by training, that's my degree. And we're always taught that you always change just one variable at a time, right? We only look at one variable at a time. And in this case, it allows us to look at a whole bunch of different variables at once. Really cool tool. There's nothing on the exam on this, but I just think I'd like to get this one planted in the back of your head. The cyclical and temporal. All right, so classes, moving on. Any questions about multivariate analysis? I can give you more information if you'd like, video or two you can look at. If so, just drop me a line. Classes of probability distribution. So this is classes of distributions. Like we have a normal distribution, which we talked about, the bell-shaped curve. It's a pattern, of how my data is going to lie. When I have a bell-shaped curve, it tells me that my process is stable and predictable. Okay. There's not a lot of outliers. Everything's falling on either side of that, the top of the bell, that line, which is the mean. And this is probability distributions are the possible values that a variable can take and how frequently they occur. All right. So normal distribution, like we talked about, the bell-shaped curve, the area is equal to 100%, shaped like a bell. It extends indefinitely in both directions and is asymptotic. I don't know what that means. The mean, the median, the mode are the same. All processes will exhibit a normal curve shape if only pure random variation exists. All right, if I have an outlier, that's something else. An example is a polar bear weighs 500 kilograms. So obviously, you ask how much a polar bear weighs, 500 kilograms, but I have to sample a lot of polar bears, more than 30, to begin to make an inference of where a polar bear weighs. And then they're going to be everywhere from 400 maybe, or to 600 to 800, but I'm going to eventually get 500 kilograms, theoretically, something around there. There's some number. It's almost like if you think about height, height in males, for example, you're going to have, a mean where the biggest number of people are going to be 5'7" or 5'8", and then you're going to get on each side of the curve, smaller numbers, and you plot it, it becomes a bell shape. The student T is another, it's probably one of the most important discoveries, because basically it's using some math where I can figure out when I don't have enough data to, like, for example, the polar bear, how can I start looking at data when I have less than 30 samples? Because think about it, remember we talked about if I don't have a bell-shaped curve, my process is running, just collect more data. A student T is a method where I can get all the advantages of a normal distribution in terms of statistics without having to have a lot of samples. So this is important when we're looking at new processes that are in R&D. But it's basically formed by combining a standard normal random variable and a chi-square random variable. And the beauty of it is it just basically it lessens the impact of outliers, right? So if I collected 15 polar bears, 25 polar bears, it's going to kind of lessen the impact of those outliers, which might be a polar bear that, you know, is 200 kilograms or 150 or something like that. Really important discovery, student T. Binomial, it's used to model discrete data. So that's data that we count, right? Continuous data is what we measure. Discrete data is what we count. And it applies when the population is large and the sample size is small. For example, flipping a coin in sets of 3, what's the likelihood of getting heads 2 out of those 3 times? So it's always going to be yes or no, heads or tails. There's always going to be 2 things that we're counting. So it's a type of distribution that we're going to use when we get into hypothesis testing for non-continuous data. And the Poisson distribution is used as for defect counts and can be used as an approximation to binomial. So again, it's for discrete data, and it's a way to see how unusual an event frequency is for a given time interval. That's kind of the most common use of Poisson distribution. An example I give is Jason Tatum is averaging 35 points a game. What is the likelihood that he will score 12 points in the first quarter of the next game? And remember, so all these distributions are about probability, right? In this case, when I'm measuring things, what's the probability? I should be able to predict my process. And F and chi-square, these are not used too much. We're going to cover them again when we get into the hypothesis test. But the F distribution, we're talking about variances from 2 different populations. Okay, from 2 different populations. So samples from 2 different populations. And basically it's a formula for variance, which is going to be our standard deviation squared of those 2 populations. An example is you're testing a new drug for heart disease called X. You want to determine the significant effects of different dosages. So you set up trials of 0 milligrams, 50 milligrams, and 100 milligrams of that drug in 3 randomly selected groups of 30 people each. And this is the case for analysis of variation, which utilizes the F distribution. Anytime you're comparing more than 2 groups, so more than 2 populations. So now if I'm going to compare maybe different heights in 2 different countries or in 2 different continents or things like that. Once the F statistic is calculated, you compare it to a table, because there's an F table. And that's, again, this is the basis for doing hypothesis tests. And then a chi-square distribution, it's when my data is asymmetrical, so it's not nice and neat bell-shaped curve. And it's used for a whole bunch of different hypothesis tests. We're going to be looking at some of that. But it tests the equality between the variance of a normally distributed population and a specific value. The example would be market researchers use the chi-square test when they need to estimate how closely an observed distribution matches an expected distribution, or if they need to estimate whether 2 random variables are independent. So, I mean, nothing on the exam on these 2. Most of our focus is going to be on these 2. And we're going to kind of touch on these 2. All right, so inferential statistics, you guys know what it is. It means we're going to make inferences regarding the characteristics of an unobservable population, every polar bear in the world, based on the characteristics of an observed sample. we rely on sample data to draw conclusions about the population from which the sample is drawn. You're going to see that sampling itself is a science with formulas, the whole 9 yards, as we go through today's slides. And statistical inference is widely used because we can't collect the entire population data. We can't get the IQ of every human being on Earth or every polar bear. Statistical inference contains two elements, the inference and then the measure of validity. And again, this is, as we're getting into hypothesis testing, it's going to sound very familiar. Clearly define the objective, decide if it's going to be evaluated by a 1 or 2 tail test, formulate a null and alternate hypothesis, select the test distribution, like what's my data, what is my data? What am I looking at here? Is it continuous? Is it discrete? Is it a normal? And then a critical value of this test statistic. Compare it to a table, and then are we going to reject the null hypothesis or no? That's inferential statistics. And the outcome is a statistical proposition about the population. So examples are estimating a population parameter, identifying an interval or a region where the true population parameter would fall with some certainty, deciding whether to reject the hypothesis made on characteristics of the population of interest, making predictions, clustering or partitioning data into different groups. There's a whole bunch of different things we can do with it. So sampling techniques, like I promised you, they turn it into a science. The population is everything, and we want to be able to make decisions on our samples. So we want to make sure our sample is representative. The process of selecting a subset of observation is called sampling, and we want to be able to collect information about a population. So sampling advantages: it's impractical or impossible to collect the entire population for obvious reasons. Don't you love these slides? Actually, I went through a whole 15-week course at the university teaching this. Man, advantages of sampling a representative subset of the population: it's lower cost, get faster data collection, it's easier to manipulate. Two major uses of sampling of samples and making statistical inference. One, estimating the population parameters using the sample statistics. For example, my weight, right? And obviously that wasn't the entire population. That was only Fridays as soon as I wake up for the last 8, I don't know, whatever, since 2006. So I'm estimating, based on, I'm estimating the population parameters based on my sample, which is Friday when I wake up. And then the second use is hypothesis testing, which is testing a statement about the population characteristics using sample data. And that's kind of what we did with the temperature in Connecticut on July 7th. And there's a bunch of different types of sampling strategies: simple random, match random, stratified, systematic, proportional to size, and cluster. Simple random samples, each item can be picked, equal chance of being selected. There's no bias involved in the sample selection. It minimizes the variation between the characteristics of samples and the population because I'm doing it randomly. And this is the basic sampling strategy. And then match random might be randomly selected in pairs, each of which has the same attribute. So for example, researchers are interested in understanding the weight of twins, or researchers are interested in understanding the patient's blood pressure before and after taking some medicine. Those would be examples of when I would do match random, before and after blood pressure, after taking the medicine. And stratified is distinct and independent categories. An individual category can be considered a subpopulation. And stratified samples are randomly selected in each category of the population. It can be gender, region, income level, anything. It requires advanced knowledge of the population characteristic. For example, a fruit store wants to measure the quality of all their oranges. So they're going to use stratified sampling by region to collect sample data. Since 40% of the oranges are from California, then we're going to collect 40% of the sample from California. If 90% of my production is on first shift, then I'm going to take 90% of my samples from first shift, 10% from second, whatever it is. That's the idea. And then systematic sampling. selected at regular intervals based on an ordered list where items in the population are arranged according to a certain criteria. Systematic sampling has a random start, and then every first item is selected going forward. Every fifth unit produced. I think this is, I know Zach's here, like SQL, right? Got that one quality guy, I think, in this group. Cluster sampling, samples are only selected from certain clusters or groups of the population, reduces cost and time, but bears the risk that the clusters are biased. For example, selecting samples from the region where its researchers are located, so the cost and time spent on traveling is reduced. And sample size is a critical element. And, this is where we just talked about the student T, being such a huge discovery. The smaller the sample size, the higher the risk that the sample didn't reflect the true population. If I weighed myself once a month, I wouldn't have the same accuracy if I did it every day, right? The greater the sample size, the more time and money we will spend on collecting samples. So we want to get the right sample size. And here's an equation for continuous data on what size sample I need to have. So I can do a Z-score, estimated standard deviation of the population, desired margin of error. And usually we're talking about continuous data, a minimum of 30 samples. And with student T, we can do 15 or 20. If calculated sample size exceeds 5% of the population, then you can discount that using this equation. And for discrete data, this is how an equation for sample size of discrete data, which is data that we count. So things like the coin toss, or what's the probability of me throwing die and getting a 5? Number of samples is going to be equal to the Z-score, the portion of one type of effect, the proportion of one type of effect not occurring, and desired margin of error. And if calculated sample size exceeds 5%, we could discount using another equation. So sampling errors, random sampling error, due to observations being selected randomly, it's inherent in the sampling process and beyond our control. Selection bias is non-random variation due to inadequate design of sampling. It can be improved by adjusting the sampling size and sampling strategy. And general concepts and goals of hypothesis testing. 340, yeah. So hypothesis tests, which we just did, we did a 2-sample t-test, in case anybody was wondering. It's a method in which a specific hypothesis is formulated about a population, and the decision of whether to reject the hypothesis is made based on sample data. And we're going to have a statistical hypothesis is formulated in pairs, null and alternative. And it tries to answer whether there's a difference between different groups or there is some change occurring. In the case of the weather, was there something different about July 7th in the rest of the sample? Are the average SAT scores from high school A and B the same? Is the error rate of one group of operators higher than that of the other? Are there any non-random causes that influence the height of kids in one state? So null is no difference, no changes occur, it's the status quo. And alternative is there is a difference. Some changes occurred, etc. So all we're going to do in hypothesis testing is either reject a null or fail to reject it. And when there's enough evidence based on the sample information, by coming up with a test statistic, we can prove the alternative hypothesis, and then we can reject the null. And there's not enough evidence, or the sample information is not sufficiently persuasive, we don't reject the null. And we talked a little bit about practical and statistical significance. An observed difference is practically significant when it's large enough to make a practical difference. So in other words, at 94 degrees, it might dehydrate more people, people might pass out more, might sweat more. That's practically significant, but it may not be statistically significantly different, is what we saw, right? The difference between 87 degrees and 94 degrees. Can you feel it? And when you walk outside after being in your office all day, that might be practically significant. And then if you do the math, it's not statistically significantly different. So an observed difference is statistically significant if it is unlikely that the difference occurred by pure chance, given a predetermined probability threshold, which was 95% surety, right? Confidence. Statistical significance indicates there are some non-random factors causing the result to take place. And the statistical significance level in hypothesis testing indicates the amount of evidence which is sufficiently persuasive to prove that a difference between group exists, not due to random chance alone. Probability refers to the likelihood, chance, or possibility of an occurrence. So the probability of any event lies between 0 and 1. The sum of all the probabilities of all possible events in a sample space is equal to 100%. Probability is always a ratio. The ratio of the chances of an event success versus total number and ways that an event can occur. So a die has 6 sides. This is an example. Sample space of 6. Each face is unique. So each time I roll a die, there's a 1 out of 6 chance that it will land on any specific number. So ways to state 1 out of 6 is 1:6 equals 1/6 equals 0.1667. It's 16.67% chance that I'm going to roll any specific number. So what's the probability of rolling 5 ones in a row? Probability is 1 equals 0.1667. 5 ones is equal to 0.1667 times 5. So not 16.67% probability, but a 0.0013 probability. So 1.3 chances out of 1,000 that I'm going to roll 5 ones in a row. And this is kind of how gambling works, right? Calculating probability allows the establishment of acceptable risk. And the p-value, again, now we're talking p-value, alpha, beta. All it means is confidence level. That's all. The rejection region. When do I reject my null hypothesis? So the p-value is defined as differences between observed data and claims made under the null hypothesis, may be real or due to chance. It's the probability of those differences occurring solely due to chance, random. So the alpha level of a test represents the threshold against which p-values are measured. And the most commonly used levels is 5%, 10%, or 1% p-value. Confidence level, as you saw in the table, most common used confidence levels are 99%, 95%, or 90%. So it's basically the inverse of what we did. So I would not pay much attention to any of this alpha, p-value, and all that. Just think rejection region, confidence level. Alpha and beta risk. A type 1 error is called a false positive, a false alarm, or an alpha error. It's associated with the risk of accepting false positives. So as we're analyzing our data, we want to make sure that try to avoid type 1 errors. It occurs when we think there's a difference between groups, but in fact there is none. For example, telling a patient he is sick when in fact he is not. And again, this is where we get into alpha and confidence intervals. Same thing, right? So 5% is the most commonly used alpha, which is the same thing as saying 95 is see it on the bottom, 100% minus the alpha. 95% is the confidence level that I'm going to use most often. And when making a decision on whether to reject the null, we compare the p-value against alpha. Type 2 error is telling a patient he is not sick when in fact he is. So these are the types of errors that we want to make. We don't want to make when we're doing hypothesis testing. And it comes down to, is my data what I think it is? Beta, same thing. The probability of making a type 2 error. So alpha is making a type 1 error. Beta is making a type 2 error. And again, 100% minus B. And the most common are going to be 1, 5, and 10. Now we're talking about the same thing in a different way. the confidence interval is where the true population parameter would fall within a certain confidence level. And most often, we're going to use 95% confidence interval. And you're going to see as we go over the next couple of weeks why it's important to pick the right confidence level, the right, set those goalposts, the right rejection region. And it's going to depend on confidence level, sample size, variability in the data. The higher the confidence level, the wider the confidence interval. The smaller the sample size, the wider the confidence interval. And the more variability, the wider the confidence interval. And again, there's the idea of the rejection region that we talked about. And this is where we're going to reject our null when our test statistic falls into that area. And so as hypothesis tests are explored, we want to keep this as a reference. This information will be explained and expanded upon ad nauseum. First is the test statistic versus the critical value. So that was the statistic that we came up with by using, the X, which was 94 degrees, and the mean and the standard deviation. And the critical value, all that means is I'm going to take that test statistic and compare it to something in a table, critical value. And then on this side, we need to know what confidence level, what the rejection region is going to be. And it's either going to be 99% confident, we're going to be 95% confident, or 90% confident. And here's a test statistic. It's a value calculated using a function of the sample. And it depends on what kind of data I'm looking at, right? Is it normal? Is it continuous? Is it discrete? Is it something that I count, something that I measure? You got to kind of understand what kind of data I'm looking at, we're looking at. So test statistics are the sample data's numerical summary to be used. And the critical value is something we take out of a table. It's something that we just look up and compare it to our test statistic. And every different type of data has different test statistics, formulas for test statistics, and different tables. And the decision rules, you guys getting tired of this same over and over? When it falls into the acceptance region, then we fail to reject the null, kind of like the 94 degrees, and we claim there's no statistically significant difference between the groups. It might be interesting to look at, in terms of climate change and looking at average temperatures and doing a test. If anybody wants to do that for a final, the final project, please let me know. That'd be kind of fun to see. See if there's statistical significant difference between 1910 or I don't know how long, they've been measuring temperature in different, maybe pick a part of the world or whatever. But when the test statistic falls into the critical region, or what I call the rejection region, then we're going to reject the null hypothesis and claim there's no statistically significant difference between the groups. When the p-value is greater than the alpha level, we fail to reject the null. Same thing, different way of saying it. And two-tail versus one-tail. Two-tail is the critical region is split into two equal parts. And again, when I do my problem statement and I say, is it significantly different than the temperature since 1950, is different than me saying, is it hotter than statistically different hotter, which would be a one-tail test. So two-tail test is used when we care about whether there's a difference. It's rejected when the test statistic falls into either half of the critical region, into the rejection region. Yeah, we already did this. So instead of alpha, we use 95%, which was the confidence level. But we set the goalpost and we look to see where our test statistic fell. And a one-tail test would be one end or the other. All right, I think I should probably get into this and get into this right now. We might only do 2 weeks on Analyze if I go good here. Things to know before using tables. I need to know the distribution classification. So am I talking about normal? Am I talking about a student T, chi-square, binomial? What is my significance level, my confidence level? What's my sample size? Degrees of freedom, all that means is the number of samples that I have minus 1. That's all degrees of freedom is, Because you're gonna see it in tables everywhere. They're gonna ask you for the DF. All it is how many samples am I looking at that, are under consideration, -1. And I gotta know if it's a right tail or left tail test. So the right tail test would be on the right of that curve, left tail, the rejection region would be on the left side of it. And we kind of read one already. This is for the Z table. The values in the table are shaded area in the curve. Rows are labeled with the Z score. And this says Z. So I'm not gonna, let me hold off on all the tables because I think we're gonna go through each of them as we introduce the each hypothesis test. All right. I told you it was like the Green Mile, this one. Any questions? Everybody, it's I think just really just focusing on those steps, to do a inferential statistics is really all you want to take away. Any questions, guys? Everybody awake?
Yeah.
All good.
All right, Marion's awake. All right, no homework. If you can, if you haven't gotten it to me, please do. I give you extra credit if you already handed it to me. Have a great rest of the day. I'll send you a recording and I'll send you the slides. We'll go from there.
All right.
Thanks, Bill.
Have a great night, guys.
Thanks.
guys.
Take care, guys.
Take it easy.
Hey.